All right, so apart from sediment cores from the seafloor, one of the ways in which we have studied glacial and interglacial periods, aside from the sediment core in the seafloor, has been through the study of ice cores, through studying the record that the ice cores contain. So many of these ice cores were obtained in Antarctica, for example, where they have recorded millions of years in terms of data, or at least several thousands, or many thousands of years. So the ice cores are typically drilled out of a glacier, and some that have been acquired have been as long as 3,000 meters in length. Thus, these ice cores record the climate history that represents more than 700,000 years, at least these ones that are 3,000 meters in length. So a large part of the so-called Ice Age from the Quaternary period is encompassed within these ice cores. So the ice cores will reveal an annual snow pattern, and this one will be preserved as different layers. So much like the tree rings in a tree, we can count up the layers within the ice cores to differentiate the ages. In those layers, which again can be counted, we can also do isotopic ratio measurements to determine the relative temperature at the time that that layer was formed. Said isotopic ratio is done by measuring the ratio between oxygen-16 and oxygen-18. So I'm going to explain this a little bit. It might take a few times for you to listen to what I'm saying, so just beware, pay attention. So remember when we talked about isotopes in chapter 18? Well, in that case, we used radioactive isotopes to date the ages of certain crystals and the units that these crystals were in. The stable isotope measurements work a little bit different than radioactive isotopes. So remember that isotopes are different representations of atoms from the same element. So this will have a different atomic mass due to the number of neutrons within their nucleus. Oxygen, in its more common form, has a mass of 16. However, two other stable isotopes of oxygen exist. There's oxygen-17, and then there's oxygen-18 as well. Out of those two, oxygen-18 is a more common one. So overall, oxygen-16 makes up 99.78% of all oxygen atoms. Oxygen-18 is 0.2%, and then the remaining amount is oxygen-17, so very minor amounts. Because the atomic mass of oxygen-18 is greater than the atomic mass of oxygen-16, it is overall heavier than oxygen-16. So, because it's heavier, it's also harder to lift. Okay, now backing up. So when evaporation of liquid water happens, HO2 becomes gaseous and is lifted up into the atmosphere. And evaporation is enhanced during warm periods, right? Evaporation happens more and more when it's warm outside than when it's cold. So when temperatures are higher, more heat and hence more energy is applied to the system, and this helps towards evaporation. With this greater energy, there is also greater potential to lift those heavier oxygen-18 atoms, as well as the oxygen-16 atoms, which means that the oxygen-18 will be more likely to also be precipitated onto the land surface when the temperatures are greater. So under glacial periods, temperatures are low, which means that there is less energy to carry the heavier atoms, which in turn also means that the precipitated water that accumulates as snow and later as ice in the glaciers is much more enriched in the oxygen-16 than in the oxygen-18, even more so than in their average occurrences, because the oxygen-18 atom is too heavy, so it won't be lifted in those cooler periods. So overall, by studying the ratio of the oxygen-16 to oxygen-18 in these ice core layers, we can deduce the temperature for the time during which that layer was formed. Okay. Another successful measurement done in the ice cores is to find the CO2 and methane concentrations at the time during which the layer of ice was formed. So CO2 is a gas typically found in the atmosphere, and it's been found to have a positive correlation with temperatures, meaning that when the temperatures are greater, CO2 concentrations are also greater in the atmosphere. CO2 gas gets trapped inside the tiny pores in between the snowflakes that later turn into the firn and then into the glacial ice. Those gases tend to be locked up in the ice unless the ice gets fractured or gets melted. And so, we can also study the concentrations of CO2 in the tiny pores of the ice layers, and with that get an idea of the temperatures at the time during which that layer formed. So, both based on the oxygen 16 to oxygen 18 ratios and on the CO2 concentrations, we have a proxy data to decipher paleotemperatures. So the image on the middle right here, it shows the isotopic ratio of oxygen 16 to 18 with change in time of up to 1 million years ago. And you can see a pretty clear period of warmer and colder weather occurring. On the bottom image here, it shows you the CO2 concentrations that were studied in the ice core dating as far back as 450,000 years ago. And it also shows you here the clear warming and cooling periods represented by those CO2 concentrations and derived to the temperatures that were positively correlated with them. So a great deal is known about glaciers and glaciation. However, the causes of ice ages are not completely understood. We know that there must have been earlier glaciations than those seen in the Quaternary period. Earlier glaciations are indicated by deposits that we call tillite. So tillite is a sedimentary rock which is formed when glacial till becomes lithified. A picture of tillite is here shown. Tillite deposits have been found to be ages as old as the Paleozoic, which is the deposits that Alfred Wegener used to support his hypothesis for continental drift. So Paleozoic lies about, or when he did that was 250 million years ago or so. And then two other even older episodes of glaciation have been dated to occur during Precambrian times, one of them being as old as 2 billion years ago, and then the other one about 600 million years ago. So any hypothesis that does attempt to explain the causes of glaciation must successfully answer two basic questions. The first question is, what causes the onset of glacial conditions? And then the second question is, what caused the alternating glacial and interglacial stages that have been documented for the Quaternary period? So one of the hypotheses for these causes of ice ages and glaciation is the hypothesis of plate tectonics. In this case, it's a hypothesis because it's not proven as a cause of glaciation. So it is, however, probably a very attractive hypothesis for explaining the fact that extensive glaciations have occurred only a few times in geologic past. So, because glaciers can form only on land, we know that land masses must exist somewhere in the higher latitudes before the ice age can commence. Glacial features seen in the southern hemisphere land masses suggest that these experienced glaciation only when they were nearer to the South Pole. For example, they were near to the South Pole during the Paleozoic era, about 250 million years ago, when all the continents were together as the supercontinent of Pangaea. And so then they experienced the glaciation period that the northern land masses didn't at the time. However, because plate movement is so slow, only a few centimeters a year, This hypothesis is not good at explaining why we saw the glacial and interglacial periods during the Quaternary period. So it's good for responding to the first question, but not for responding to the second question. Another process that may trigger climate change on a scale a little bit closer to thousands of years rather than millions of years, like the plate tectonics hypothesis did, is needed in order to answer why we had the interglacial and glacial cycles of that Quaternary period. So today, many scientists believe that these cycles were linked to variations in the Earth's orbit. This hypothesis was developed by a Serbian astrophysicist called Milutin Milankovic, and is based on the premise that variations in incoming solar radiation are a principal factor in controlling the Earth's climate, meaning the sun is going to be one of the main drivers for temperature controls on the Earth's climate. So Milankovic formulated a mathematical model based on the following elements. The first one is the variation in the shape of the Earth's orbit about the sun. This is called the eccentricity of the Earth, and it is showed by the image here in the top right. So I'll explain it in a second. The second element is the change in the obliquity. So these are changes in the angle that the Earth's axis makes with the plane of our Earth's orbit, and as this is seen on this image here. And then the third element that he used was the element of precession, which is the wobbling of the Earth's axis, and it is represented by this bottom middle image here. So by this formulation, the three variations in the Earth's orbit are called Milankovic cycles, after the Serbian astrophysicist that came up with them. Okay, so Milankovic cycles. So from these cycles, a time of minimum and maximum temperatures based on seasonality can be found, which is what Milankovic did when he formulated this mathematical idea. So using the Earth's eccentricity, first of all, when the orbit around the sun is more elliptical than it is circular, then the temperatures are colder on a seasonal basis, meaning when the Earth is further from the sun, it's going to be colder if the orbit is more elliptical than when it is circular. So the Earth is going to go from a more circular orbit to a more elliptical one, and back again to a more circular one every 100,000 years or so. That's the eccentricity cycle. Using the obliquity changes, when the tilt is greatest, meaning around 24.5 degrees on the plane of revolution, then the seasons are more pronounced. So winter is colder and summer is warmer. The cycle of the Earth's tilt going from 21.5 to 24.5 and then back to 21.5 is about 41,000 years. And lastly, using the precession, some parts of the Earth will be colder than others as the wobbling point to a different direction, or as the wobbling will point to a different direction during a cycle that lasts 26,000 years. So all of these have different cyclicities, but a combination of the three of them can make certain points in time be colder than other points in time. So we'll now take a look at the two videos that I have here for you. The first one just explains precession, or the wobbling of the Earth's axis, which I think is a little bit hard to visualize. So this video also shows you some astrological signs and such. I'm going to go ahead and skip this part of the video as it does not add anything to the understanding of the cycles themselves and how they have to do with the temperatures observed.